So this problem reads, a galvanic cell consists of an Mg electrode and a 1.0 mole per liter MgNO3 solution and an Ag electrode and a 1.0 mole per liter AgNO3 solution. And the question is, calculate the standard EMF of this cell at 25 degrees Celsius. So let's just start pulling apart this problem. First, we're calculating EMF, and how can we do that? We can take E of the cell is equal to the E of the cathode minus E of the anode, and by E, it's the standard reduction potential. So it's the cathode minus the anode relating to the standard reduction potentials. What exactly are we dealing with here? While you may see MgNO3 you might see AgNO3. The NO3 is not very important. What we're concerned about is the electrodes with the Mg and the Ag. So first step, so now we're actually going to start working it. First step is to write out the standard reduction potentials of both Ag and Mg. These values are nothing you calculate. They should be given to you in some sort of table. For the purpose of this equation, I'm just going to write them down, but what I'm writing is something you can take directly from a table that most likely will be given by your professor. Sorry. So I'm just writing down what would be given in your table. And I'm writing them how they would actually be listed from the highest value to the lowest value. So the Ag standard reduction potential is higher. It is at 0.80 volts. Compared to the standard reduction energy of Mg, which is negative 2.37 volts. So this is how it would be. It would look very similar. They would be in this kind of order on the table that you would look at. So now we can use the diagonal rule. And the diagonal rule will just let us know kind of like if this would even go to reaction and how it would, what would be in your reactant, what would be in your product. So you would take the top one, you'd go top left, and if you drew a diagonal line, bottom right, those two are going to be together in your reactant, and then what's left will be in your product. So you should write it as such. So if this is going to be, if Ag plus 1 electron is going to be my reactant, you can write it as such. And then you can write, we'll just do the top one first. So you're going to want to keep them separated. And then Mg is going to, Mg as a solid is going to want to be in your reactant as well. So we're just going to set it up almost like we're about to put them together. Okay, so you could add them together to get your overall equation, which I am not going to do because it is not necessary to calculate the standard EMF. What I think is most important is kind of looking at where the electrons are in each situation, because we need to establish what is the cathode and what is the anode. So I'm going to give a little tip. So something that is being reduced, the cathode, and something is being oxidized is an anode. So you might just want to kind of remember that. It's helpful. By reduced, when you're reducing something, you are adding electrons to make it more negatively charged. When something is oxidized, you're removing electrons to make it more positively charged. So you can look at the what we have set up here, and you can tell which one is the cathode and anode based off of where they have placed the electrons. So in this case, when you look at Ag plus 1 electron, the electron is in the reactant. So if you were to like read it, you'd say Ag plus an electron. So what are you doing? You're adding electron, thus you're reducing it. Remember, reducing is increasing the number of electrons. So right away we can say, oh, this is our cathode. Because again, it's adding electrons. And off of elimination, you can determine that Mg is your anode. Also, you can tell you have your electrons in your product, which means you're releasing electrons. Again, oxidized, it's becoming more positive. It's losing electrons, so it's in your product, so you're losing the electrons. Thus, the Mg is the anode. So you could, I'm not going to combine them for the sake that it's not necessary for this problem, but for others it is necessary to combine your two, having like Ag plus Mg, the solid, and you have to balance your electrons, blah, blah, blah. I'm not going to go over it, but so basically from here you have your cathode and your anode, and you've already established what the standard reduction potentials are for each. So again, we're just going to copy this just so you can visualize it. This is your cathode. I'll put cathode right here. And Mg is your anode. I'll put anode here. Hope that's not too squished. And all you have to do now is put in your values. So E of the cell is going to equal to the cathode, which is 0.80 volts, minus, and I'd put parentheses here so that you keep your signs correct, because as you can see there's a negative here in your anode, so minus the anode. So yeah, just be careful with the sign, and from here it's really just simple math. And when you do the 0.8 volts minus the negative 2.37 volts, you get 3.17 volts. And this is your answer. This is the standard EMF of the cell.